In the previous sessions, we have looked at area under a curve, and we have seen the volume of the solid of revolution. Now let's look at the surface area of solid of revolution. So given a curve y is equal to f of x on the interval a to b, where f is continuous and differentiable and f of x is greater than or equal to 0. The radius is always non-negative. Now the curve f of x generates a surface when revolved around the x-axis, bounded by x equal to a and x equal to b. So when we revolve it, we get this surface. Let us say this point is C, and let's say this point is Q. So here the x value of C is A and x value of Q is B. Now let P is equal to x comma y be a point on the curve. So if P is equal to x comma y, then Q is equal to x plus delta x comma y plus delta y. So arc PQ has a length delta S. When this arc is revolved around the x-axis, it produces a thin frustum. You can look at frustum as a thin slice. Its surface lies between the surfaces of two cylinders. Which two cylinders? So here, when P is revolved around the x-axis, it will generate a circle. Similarly, Q, when revolved around the x-axis, will generate a circle. This is one and this is the other one. Now, we treat this circle, which is generated by P, at the base of a cylinder. Let's bring it up. Similarly, we can treat this purple circle as the base and draw a cylinder. So here the surface generated by revolving the arc PQ around the x-axis lies between these two cylinders, surfaces of two cylinders. And just to make it complete, let's draw this circle also so that we can see the ends. Now inner cylinder with radius MP. So this is the radius of the inner circle or inner cylinder. Similarly, outer cylinder has a radius NQ. So inner cylinder with radius MP is equal to Y, because remember P coordinates is x comma y. Outer cylinder with radius NQ and Y coordinate of Q is Y plus delta Y. Since the required surface lies between the surfaces of these two cylinders, we have an inequality. Now the surface area of the cylinder is 2 pi r h. So the inequality would be 2 pi times y times delta s is less than the surface generated by the arc, that is delta capital S, which is in turn less than 2 pi times the radius of the outer cylinder, that is y plus delta y, times the arc length, 2 pi r h. So the surface generated by this arc lies between the surface of these two cylinders. Now let's divide throughout by delta small s. We get 2 pi y is less than delta s capital divided by delta s smaller, which is in turn less than 2 pi times y plus delta y. As delta s goes to 0, that means the arc length goes to 0. So which means I keep taking closer and closer to Q. So the arc length keeps reducing. The two radii become equal. So as I keep taking it closer and closer and closer to Q, the radii become equal, which means delta x and delta y goes to 0. Now we take the limit as delta s goes to 0 of delta cap s by delta small s, which would be equal to ds by ds, which is equal to 2 pi times y, which implies that d cap s, that is the change in the surface, is equal to 2 pi times y ds. So to get the total surface area generated from x equal to a to x equal to b, we integrate both the sides. So s is equal to 2 pi times the integral from a to b of y ds. Now, since we are revolving around the x-axis, we have to write this integral in terms of x. And we know that ds by dx is equal to square root of 1 plus dy by dx square. So our final result becomes the surface area is equal to 2 pi times the integral a to b of y times the square root of 1 plus dy by dx square dx. So that was the surface area of solid of revolution, and this is the formula we use to arrive at it. In the next session, we will look at a specific example and arrive at the surface area. I think we will look at the surface area of the sphere itself. If you found this useful, don't forget to like, share, and subscribe. Questions, suggestions, and opinions are always welcome. Thanks for watching. See you in the next session. That's it for now.